Tonight, we're going to explore something that sounds simple, but is actually one of the most mind-bending ideas in all of science: cosmic time travel. You've probably seen it in movies or heard scientists mention it in passing. But here's what most people don't realize. When you truly begin to understand what time travel through the cosmos would involve, when you grasp how space and time bend together, it changes how you see the universe itself. This is not just a clever story or a fun thought experiment. It's an idea so vast and strange that it challenges what we think is possible. And by the end of this journey, you're going to understand exactly why scientists study it and why ordinary ways of thinking about time simply don't work. Before we go any further, if you enjoy deep, careful explorations like this, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Time is something humans experience every day. We feel it in the rhythm of our lives, in the rising and setting of the sun, in the beat of our hearts and the passing of seasons. Yet the time we sense is only a shadow of its true nature. In physics, time is not just a way to measure change. It is a dimension, a fundamental part of the structure of reality. Just as space has length, width, and height, time is the fourth dimension, intertwined with space into a single fabric known as space-time. It is not merely a river flowing in one direction, but a quantity that can stretch, shrink, and bend depending on motion and gravity. To understand cosmic time travel, we must first understand what time really is, beyond human perception. Isaac Newton first described time as absolute. He imagined a clock ticking steadily, unaffected by events, flowing the same for all observers. According to this view, a second on Earth was the same as a second on Jupiter or a distant star. Time was a universal backdrop, a silent stage on which all events played out. For centuries, this idea allowed scientists to calculate motion, predict the paths of planets, and build the foundation of classical mechanics. It seemed simple, tangible, and reliable, but the universe is not always simple. When Albert Einstein introduced his theory of relativity, the absolute view of time dissolved. Time was no longer uniform. It became linked to motion and gravity, a variable that changed depending on speed and the presence of mass. Two observers moving at different speeds could measure different durations for the same event. A clock on a fast-moving spaceship would tick more slowly than one on Earth. This phenomenon, called time dilation, is not theoretical. It has been confirmed repeatedly through experiments with high-speed particles and precise atomic clocks aboard satellites. Time became a relative quantity, flexible and responsive to the universe itself. To grasp time, one must also understand measurement. Every experiment, every observation depends on a clock. Ancient civilizations used the sun and moon to track days and months. Modern science measures time with astonishing precision using atomic transitions in cesium atoms, which define the second to billionths of a second. These measurements allow physicists to detect minuscule differences in time caused by velocity and gravity. They also form the backbone of technologies such as GPS, which require exact timing to determine position on Earth. Without precise measurement, cosmic time travel would remain an abstract idea, impossible to verify or understand. Time in physics is deeply linked to causality. Causes precede effects, and the order of events is critical. When physicists speak of time, they refer to sequences that obey this principle. Moving forward along this sequence is natural, but moving backward raises paradoxes. The idea of turning back time is tempting in thought experiments, but it is constrained by physical laws. In cosmic terms, the past exists as a fixed set of events, while the future unfolds with probabilities influenced by physical conditions. Understanding this distinction is crucial for exploring time travel scientifically rather than imaginatively. Even on Earth, time does not flow uniformly. Clocks at different altitudes run at slightly different rates due to gravitational time dilation. This effect, predicted by Einstein's general theory of relativity, has been measured directly. A clock on a mountaintop ticks slightly faster than a clock at sea level. The difference is tiny, imperceptible in daily life, but measurable with modern technology. In cosmic environments with much stronger gravity, such as near neutron stars or black holes, the difference becomes extreme. Time can slow to a fraction of its normal rate, illustrating that time is not an independent backdrop, but a property shaped by matter and motion. Time is also intimately connected to space. Moving through space affects the passage of time, and vice versa. This relationship is encoded in the concept of space-time intervals, which combine spatial distance and temporal separation into a single measure. Events that are simultaneous for one observer may not be simultaneous for another moving at high speed. The universe does not offer a single universal clock. Instead, each observer carries their own measure of time, dependent on their state of motion. This is a cornerstone of relativistic physics and a foundation for understanding cosmic time travel. The flow of time is experienced as continuous, but physics allows us to consider it in discrete intervals when necessary. Light, for example, travels in finite steps across space. Every observation we make of the universe involves light or other signals arriving after a delay. In this sense, seeing distant stars and galaxies is already a form of time travel. The further away an object is, the older the light we observe. A star, A, 1,000 light years away, is seen as it was 1,000 years ago. The cosmos is a vast archive, and time is the key that unlocks these layers of past events. Even within our own solar system, the finite speed of light creates measurable differences. Signals from spacecraft like Voyager and New Horizons take hours to reach Earth. Astronomers account for this delay when sending instructions and receiving data. The speed of light sets a fundamental limit on information transfer, connecting time directly to distance. Observing the universe means looking back, and any attempt to manipulate time requires acknowledging this intrinsic link between space and time. Time is not separate from the universe. It is woven into every motion and every interaction. Understanding time also requires appreciating its connection to entropy. The second law of thermodynamics defines the arrow of time. Systems naturally evolve from order to disorder. Ice melts, stars burn fuel, and galaxies drift apart. This directional flow gives time its familiar one-way quality. Without it, concepts like memory, causality, and history would have no meaning. Entropy is subtle yet pervasive, linking microscopic processes to cosmic evolution. The progression from low entropy to high entropy is a universal clock, marking the irreversible passage of events. As we consider cosmic time travel, it is essential to recognize that time is not a single uniform river. It is a flexible dimension, influenced by speed, gravity, and the distribution of matter in the universe. Clocks tick differently depending on location and motion. Light carries information from the past across vast distances. Entropy marks the irreversible progression of events. In the next step of our journey, we will explore how light itself acts as a time machine, allowing us to see the universe not as it is now, but as it was millions or even billions of years ago. Every photon that reaches our eyes or our instruments is a messenger from the past, bridging space and time in a way that brings cosmic history within our grasp. Light is the universe's messenger. It carries information across space, traveling at a speed so fast it seems instant to our daily senses, yet across cosmic distances, it moves slowly enough that it reveals the past. Every photon of light that arrives at Earth has a story. It has journeyed for years, decades, centuries, or even billions of years, traversing empty space, weaving through gravitational fields, bending around massive objects, and finally reaching our instruments or our eyes. The finite speed of light, approximately 300,000 kilometers per second, is not a limitation. It is a window into history. Every observation we make is inherently a glimpse backward in time, a record of how the universe once appeared, rather than how it exists now. The Sun, our closest star, provides a clear and immediate example. The light from the Sun takes about 8 minutes and 20 seconds to reach Earth. When we look at the Sun, we see it as it was just over 8 minutes ago, not as it is at the exact instant we perceive it. The delay is imperceptible in everyday life, but it demonstrates the principle. Even within our own solar system, light defines the way we experience time. Observations of the Moon, the planets, and asteroids are all observations of events that have already happened. Tracking Jupiter's moons, for example, involves measuring light that departed hundreds of seconds ago. Time, in this sense, is layered, with each observation a moment pulled from the past. As we extend this view to stars beyond our system, the effect becomes profound. The nearest star system, Alpha Centauri, is over 4 light-years away. That means the light we see from it today began its journey long before we were aware of our own solar system's place in the galaxy. For distant stars, the gap widens. When astronomers study the Andromeda galaxy, over 2 million light-years away, they are observing it as it existed 2 million years ago. Its stars, nebulae, and spiral arms are all historical records, frozen in the light that has traveled across unimaginable distances. Each photon is a chronicle, and each telescope is a tool to read the story. Telescopes act as time machines, allowing humans to peer into epochs long past. Large observatories, both on Earth and in space, collect light from distant objects and focus it into images and spectra. These instruments transform faint glimmers into detailed maps of galaxies, clusters, and the cosmic web. By analyzing the properties of light, scientists can determine the age, composition, temperature, and motion of celestial objects. Spectroscopy, the study of light split into its component colors, allows astronomers to detect elements in stars that may have existed billions of years ago. A telescope does not merely magnify, it records time itself. The concept of the light year emerges naturally from this relationship between distance and time. A light year is not a measure of length in the conventional sense, though it is often treated that way. It is the distance light travels in 1 year. This unit ties spatial measurement directly to temporal measurement, reinforcing the idea that observing distant objects is observing the past. A galaxy 10 million light-years away is seen as it was 10 million years ago. The light has traveled uninterrupted across voids, sometimes deflected by massive clusters of matter, but always retaining the story of its origin. In this way, distance and time are inseparable when looking into the cosmos. The same principle applies even to planets within our solar system. Images of Mars taken from Earth are slightly delayed. Signals sent to rovers on the Martian surface require minutes to traverse the space between planets. light carries both visual and informational delays. When we operate spacecraft, monitor planetary weather, or study atmospheric phenomena, we are always working with the past, even if the delay is only a few minutes or hours. Cosmic time travel, in this sense, is already a part of human technology. Distant stars provide even more striking examples. Light from stars hundreds or thousands of light years away shows them as they were long before modern humans existed. Some of these stars may no longer exist. They may have exhausted their fuel, collapsed into white dwarfs, or exploded as supernovae. The light that reaches us is all that remains of their history, traversing time and space to reach our instruments. By studying these stars, scientists reconstruct stellar life cycles, galactic evolution, and the chemical enrichment of the universe. The act of observation becomes an archaeological process, peeling back layers of time to reveal the past. Nebulae, the clouds of gas and dust where stars are born, illustrate this even further. The Orion Nebula, visible to the naked eye, is over 1,300 light-years away. Photons arriving from its glowing gases have traveled for over a millennium. The stars forming within it are observed as they were centuries ago. Light carries the signature of chemical reactions, the temperature of gases, and the motion of matter, all frozen in transit. Astronomers interpret this information to understand processes that unfold over millions of years, constructing models of stellar birth and evolution. Time and space converge in every observation. Galaxies, billions of light-years distant, extend this principle to cosmic scales. When we observe these massive collections of stars, we see entire systems as they existed long before Earth itself formed. The Hubble Space Telescope and other observatories capture photons that began their journey shortly after the universe emerged from its earliest, hot, dense state. The oldest galaxies observed provide a glimpse of a universe only a few 100 million years old, a young cosmos emerging from darkness. Each image is not merely a picture. It is a record of cosmic history, encoded in light that has traveled across space and time. Even phenomena such as supernovae and gamma-ray bursts, which occur over days or minutes in their own frames of reference, are seen with delay. The light from a supernova in a distant galaxy may take millions of years to reach Earth. By the time we observe it, the event is long finished at its origin. Astronomers can calculate when and where the explosion occurred, reconstructing events that are completely removed from present-day experience. In this way, the cosmos continually allows humans to witness events across time, effectively observing history as it unfolds across vast distances. The finite speed of light also sets a universal speed limit for information. Nothing can travel faster than light, so no signal or object can convey information instantaneously across the universe. This principle ensures that the past is always accessible, but the future remains out of reach until light from more recent events arrives. Cosmic observations are thus inherently historical, a constant reminder that looking outward is looking backward. Every star, every galaxy, every cosmic event observed is a chronicle written in photons, each one a message sent across the expanse of space and time. Time, when mediated by light, becomes measurable on cosmic scales. Distances and durations merge. Observing the Sun, we see it 8 minutes in the past. Observing distant galaxies, we see millions or billions of years into the past. Light is the bridge, carrying information, preserving history, and connecting the present observer to distant events. In this sense, the universe is a vast library, with each photon acting as a page, each telescope as a reader, and each measurement as a record of history. Cosmic time travel is embedded in the very act of seeing. Even as we examine nearby stars or galaxies, the principle scales without limit. Every point of light in the night sky is an image of the past. The Milky Way itself contains stars whose light has traveled thousands of years before reaching us. The motions of these stars, their birth, their deaths, and their chemical transformations are recorded in the light that finally arrives at Earth. The universe, though immense and often incomprehensible in scale, presents itself in layers of time, each accessible to observation, analysis, and understanding. By understanding light as a carrier of temporal information, scientists can reconstruct cosmic history, observing different wavelengths from visible light to radio waves, infrared, ultraviolet, and X-rays, provides additional context about processes invisible to the human eye. Each wavelength offers a different perspective on cosmic events, revealing details of temperature, density, motion, and composition. Light is not just an image. It is a messenger of physical conditions, a record of processes, and a measure of time elapsed since emission. Through this lens, every observation is a journey backward, every measurement a step into the past. The interplay of light and time forms the foundation of all astronomical knowledge. Without the finite speed of light, distances would be meaningless, observations would be instantaneous, and history would be obscured. With it, humans can study the universe's evolution, from the formation of stars to the assembly of galaxies, and even glimpse the earlier stages of cosmic structure. Telescopes, sensitive detectors, and spectrometers all serve the same purpose: to capture photons and decode the time embedded in them. Through this process, humans become observers of a timeline that spans billions of years, witnessing events far beyond the reach of direct experience. Cosmic time travel, in this form, is not science fiction. It is the act of observation. Every photon arriving from the sky is a record of the past, every measurement an entry in the universe's history. From the Sun to the most distant galaxies, light allows humans to trace the steps of cosmic evolution, to understand processes that occurred long before Earth formed, and to perceive events that would otherwise remain inaccessible. By following light, scientists travel through time with precision, reconstructing the universe's story across both space and centuries. In this way, light is more than energy. It is a temporal bridge, a carrier of information, and a natural time machine. The further the distance, the deeper the history, and the more powerful the insight. Observing the night sky is therefore an act of cosmic archaeology. Each observation, each spectrum, each image captured by humanity's instruments is a direct encounter with the past. Time and distance, inseparably linked by light, reveal the unfolding narrative of the cosmos, allowing humans to witness events that no mind could imagine, and no imagination could reach without the aid of photons traveling across the vast expanse of space. Time does not flow in the same way for everyone, everywhere. This principle became clear when Albert Einstein formulated his theory of special relativity in the early 20th century. He asked a simple question: what happens to measurements of time and space for objects moving at high speeds? In everyday life, differences are negligible. A car, a plane, or even a rocket within Earth's atmosphere travels too slowly for relativistic effects to be noticeable. But as objects approach the speed of light, time itself stretches and contracts. Einstein's insight was that motion changes the measurement of time, linking it intimately to velocity and forcing a rethinking of the universe's fundamental structure. In special relativity, time is relative. Two observers moving at different speeds will not agree on the duration of events. Imagine a clock on a spaceship moving near the speed of light. An observer on Earth sees that clock ticking more slowly than a stationary clock beside them. The faster the spaceship moves, the greater the difference. This effect, called time dilation, is a direct consequence of the principle that the speed of light is the same for all observers, regardless of their motion. No matter how fast you travel, light always moves at a constant speed, and the universe compensates by stretching time and contracting distances. Time dilation is not a theoretical curiosity. It has been measured repeatedly in the laboratory. Subatomic particles called muons, produced when cosmic rays strike the atmosphere, decay quickly in their own rest frame. However, when they travel close to the speed of light toward Earth's surface, their observed lifetimes increase dramatically. These particles reach the ground in numbers far greater than classical physics would predict. The difference is explained precisely by time dilation. The fast-moving particles experience less time than stationary observers, confirming that time is flexible and depends on motion. Human technology also confirms the reality of relativistic time. Global Positioning System satellites orbit Earth at high speeds and at altitudes where gravity is slightly weaker than on the surface. Both velocity and gravity affect time, and engineers must account for these effects to maintain accurate positioning. Without correcting for relativistic time dilation, GPS errors would accumulate quickly, making the system unreliable. Every day, satellites demonstrate that time is not uniform, and that clocks in motion or in different gravitational potentials measure time differently. The union of space and time is another consequence of relativity. Space and time cannot be treated separately. Events occur at specific points in space and at specific moments in time. Together, they form space-time, a four-dimensional fabric in which the universe exists. Motion through space affects motion through time, and vice versa. A traveler moving through space at high velocity is also moving differently through time relative to a stationary observer. This interconnectedness explains why relativistic effects arise. Moving faster through space means moving slower through time. The universe maintains a balance between space and time to preserve the speed of light as an absolute limit. Special relativity also predicts phenomena that are subtle yet profound. Length contraction occurs alongside time dilation. Objects moving at speeds close to light appear shorter along the direction of motion to stationary observers. Both length contraction and time dilation are necessary consequences of the invariance of the speed of light. They are not illusions or tricks. They are measurable effects that appear whenever objects approach relativistic speeds. Together, they reshape our understanding of motion, duration, and the fabric of reality. Time travel to the future, in this context, is not a paradox. It is a natural outcome of relativistic physics. An astronaut traveling at near light speeds will age more slowly than people who remain on Earth. Upon returning, the astronaut may find that years or decades have passed at home, while only months or years have passed for them. This is not imagination. It is a direct prediction of Einstein's equations, confirmed by experiments with high-speed particles and precise clocks on jets and satellites. Moving forward in time faster than the stationary world is a physical reality, achievable within the laws of nature. The flexibility of time also affects communication and synchronization across space. Signals sent between rapidly moving spacecraft and Earth require precise timing adjustments. Engineers must account for the relative motion of both sender and receiver, or measurements become inaccurate. Even light itself, traveling at a constant speed, interacts with these effects. Observers in different frames of reference experience time differently, yet the universe remains consistent. Special relativity provides the mathematical framework to reconcile these differences, making reliable space travel, communication, and navigation possible. Time dilation has practical consequences in particle physics. High-energy accelerators propel particles to speeds approaching light. Their lifetimes increase as observed from the laboratory frame, allowing experiments that would be impossible if time were absolute. Particles that decay in fractions of a second in their rest frame can survive long enough to be detected, studied, and manipulated. Experiments at facilities like CERN repeatedly demonstrate that time is not universal, but depends on the observer's frame of reference and relative motion. Even simple motions, when scaled to cosmic velocities, produce dramatic temporal effects. Consider a spacecraft traveling to the nearest star system at 90% of the speed of light. While the journey might take decades from the perspective of those remaining on Earth, the travelers would experience only a fraction of that time. Their biological clocks, instruments, and communication systems all tick more slowly relative to Earth. Relativistic physics turns the concept of time travel into a practical calculation, rather than a fantasy. It is measurable, predictable, and unavoidable once speeds approach light. The concept of simultaneity is also reshaped by relativity. Two events that occur at the same time in one frame of reference may occur at different times in another. This relativity of simultaneity means there is no absolute now across the universe. Each observer carries their own measure of time, defined by their motion and position. The fabric of space-time is a dynamic arena where motion, gravity, and distance influence the flow of time. Understanding this is essential to predicting outcomes and planning journeys across relativistic distances. As humans contemplate interstellar travel, these effects become significant. Any mission to nearby stars at relativistic speeds will produce measurable differences in aging and time experienced by astronauts. Communication with Earth will experience delays and time offsets. Calculations must include both velocity-based time dilation and gravitational time effects from massive bodies encountered along the path. Spacecraft engineers and physicists use the mathematics of special relativity to design feasible missions and predict how time will pass for travelers versus observers at rest. Time dilation is not uniform across the universe. It varies with speed and gravitational potential. A clock on a high-speed spacecraft experiences different temporal flow than a clock on a stationary planet. Similarly, clocks closer to massive objects experience slower time relative to those farther away. These variations are not theoretical abstractions. They are verified in laboratories, satellites, and particle accelerators. The universe enforces them consistently, demonstrating that time is a physical quantity, measurable and manipulable through motion and gravity. Space-time diagrams used in physics illustrate these effects visually. World lines trace the path of objects through space and time, revealing how motion stretches and bends the timeline. The geometry of space-time predicts not only time dilation, but also limits on acceleration and velocity. No object with mass can reach the speed of light, yet as speeds increase, the flow of time slows predictably. These diagrams provide scientists with tools to calculate temporal effects precisely, allowing theoretical predictions to match experimental observation. Even light itself is affected indirectly by relativity. While it always travels at the same speed, the perception of time along its path is different for observers in motion, relative to the light source. Moving clocks run slower, stationary clocks run faster, and the universe maintains internal consistency. Light becomes a reference, a cosmic constant, against which all relative motion is measured. Its unchanging speed provides a foundation for understanding time's flexibility, allowing humans to predict the flow of events across space. The implications for future space travel are profound. If humans ever travel at relativistic speeds, they will experience journeys that feel shorter than the time elapsed on Earth. Future generations on Earth could observe travelers return after decades or centuries have passed, while the travelers themselves have aged only a few years. Time travel into the future through motion is therefore not only possible but inevitable once relativistic velocities are achieved. It is a scientific certainty rooted in the geometry of space-time, confirmed by both thought experiments and real-world measurements. Einstein's theory thus transforms time from a fixed, universal backdrop into a dynamic, flexible dimension. It is influenced by motion, speed, and the relative positions of observers. Clocks are no longer absolute. They are measures of local time, shaped by circumstances and environment. Observers in different frames will disagree on durations, yet the universe obeys precise, predictable laws. Time travel into the future is real, measurable, and entirely consistent with physics. The flow of time, once assumed to be uniform and inevitable, is now understood as relative, opening the door to journeys that extend beyond human intuition and into the vast stretches of cosmic possibility. Through special relativity, humans gain the ability to comprehend the temporal consequences of motion. We can predict how fast time will pass for astronauts, particles, or instruments moving at high speeds. We can reconcile observations across frames of reference and measure the effects with exact precision. This knowledge forms the foundation for cosmic time travel, not as fiction, but as a tangible, calculable effect, rooted in the laws of nature and confirmed through both laboratory and celestial observation. Gravity shapes not only the paths of planets and stars, but also the flow of time itself. Albert Einstein's general theory of relativity revealed that mass and energy warp the fabric of space-time. Imagine space-time as a stretched sheet of elastic. When a heavy object, like a planet or star, sits on this sheet, it creates a depression. Other objects move along the curves created by this depression, and even light bends as it passes nearby. But this curvature affects more than motion. It also affects time. Clocks closer to massive objects tick more slowly than clocks farther away. Gravity, it turns out, is a sculptor of time. This effect, called gravitational time dilation, is subtle in everyday life but measurable. On Earth, clocks at different altitudes run at slightly different rates. A clock at the top of a mountain, farther from the planet's center, ticks faster than a clock at sea level. The difference is tiny, fractions of a second over a year, but precise instruments can detect it. Atomic clocks, which measure time using the vibrations of atoms, confirm these differences consistently. The stronger the gravitational field, the slower time passes. Earthbound experiments demonstrate that time is not universal. It is shaped by the presence of mass. Gravitational time dilation is more than a laboratory curiosity. It has practical implications for technologies like GPS. Satellites orbit Earth at altitudes where gravity is weaker than on the surface, and they move at high speeds. Both effects influence the passage of time on board. Engineers must correct for these differences to maintain accurate positioning. Without accounting for relativistic effects, GPS errors would accumulate rapidly, making navigation unreliable. Every day, our technology operates within a framework defined by gravity's influence on time. The effect becomes extreme near massive objects, such as neutron stars or black holes. A neutron star packs the mass of the Sun into a sphere only a few kilometers across. The gravitational field at its surface is immense. A clock near the star's surface would tick far more slowly than a clock at a safe distance. Time itself stretches, bending along with space. In such environments, the difference between seconds for a nearby observer and years for a distant observer can be enormous. The universe allows these extreme variations, demonstrating that time is a flexible dimension, not a fixed constant. Black holes represent the most extreme example of gravitational time dilation. At the event horizon, the boundary beyond which nothing can escape, time appears to stop for a distant observer. A person falling toward a black hole would experience time normally along their own path. But to someone watching from afar, the fall would seem to slow infinitely. Signals emitted during the descent stretch fade and shift toward longer wavelengths, appearing frozen as the event horizon is approached. Gravity has warped space-time so dramatically that the usual rules of time break down from the outside perspective. The difference in time flow between observers is not imaginary. It is a direct consequence of the geometry of space-time. Einstein's equations predict precisely how clocks behave near massive objects. Satellites, orbiting stars, and planetary probes all follow these rules. By comparing clocks at different distances from a gravitational source, scientists can measure the curvature of space-time and confirm general relativity. These experiments have been repeated countless times, from terrestrial laboratories to space-based observatories, each confirming that gravity shapes both space and time. Even falling into a black hole illustrates time's flexibility. The traveler experiences seconds, minutes, or hours normally, while distant observers see the process slow to near eternity. The tidal forces near the black hole grow immensely, stretching and compressing objects in ways that make survival impossible. Yet the passage of time remains relative. This duality, normal experience locally, extreme dilation externally, reveals the depth of relativity's consequences. Time is not a universal metronome. It is dependent on context, motion, and gravity. The effects of gravitational time dilation also appear in more familiar cosmic settings. White dwarfs, the remnants of stars like our Sun, have intense gravity at their surfaces. Clocks near these stars run more slowly relative to clocks in space far from the star. Binary systems, where a white dwarf orbits another star, provide natural laboratories for measuring time differences. Observations of pulsars, rapidly spinning neutron stars, also allow precise tests of relativity. The timing of pulses, influenced by strong gravity, confirms that time bends in the presence of mass. Even modest differences in gravitational potential produce measurable effects. Experiments using atomic clocks placed at different floors of tall buildings can detect time differences. Clocks separated by just a few meters tick at slightly different rates. While the effect is minute, it is real, quantifiable, and predictable. Time is not absolute. It responds to the curvature of space-time. Gravity, therefore, is not only a force, but also a governor of temporal flow, shaping every event, every process, and every measurement. Black holes, with their extreme curvature, serve as laboratories for the most dramatic consequences of gravitational time dilation. At the singularity, where density becomes infinite, space-time curvature also becomes infinite, and the known laws of physics break down. Observers approaching this point encounter enormous gravitational gradients. Locally, time progresses normally, but externally, the approach is frozen in time. photons emitted from near the singularity stretch to extreme wavelengths, effectively erasing signals. Time, near a black hole, becomes a relative experience, governed by the immense mass concentrated in an infinitesimal volume. The combination of motion and gravity complicates time further. A spacecraft orbiting near a black hole experiences both its velocity and the intense gravitational field. Both effects slow time relative to a distant observer. Calculations using general relativity can predict exactly how much slower the clock will tick. These predictions have been tested using pulsars orbiting massive companions, confirming Einstein's theory across cosmic scales. The closer to the massive object, the more pronounced the effect. Gravity warps time, stretches it, and bends it, just as it warps space. Gravitational lensing, another consequence of general relativity, illustrates time's interconnection with space. Light passing near massive objects bends along space-time curves. This bending delays the arrival of photons, effectively lengthening the travel time. Observing distant galaxies through gravitational lenses allows astronomers to measure these delays and verify predictions of time dilation. Even across vast distances, gravity imprints itself on the flow of light and the measurement of time, revealing the depth of spacetime's curvature. Experiments in Earth orbit also confirm these effects. Clocks aboard satellites experience both gravitational time dilation from being farther from Earth's mass and time dilation from their orbital speeds. The combined effect is measurable and must be corrected for accurate navigation and communication. General relativity is not a theory of speculation. It is a practical framework, necessary for technologies that rely on precise timing. Time bends, stretches, and slows in predictable ways wherever mass is present. Near a black hole, these effects reach their maximum. The event horizon is a surface where the escape velocity equals the speed of light. To a distant observer, an object approaching this surface seems to slow stretching signals across time. The closer the object gets, the more extreme the stretching. Yet locally, the object experiences time normally, falling toward the horizon in finite time. This divergence of perception between observers illustrates the relativity of time under strong gravity. Time is no longer a single flow. It becomes a measure that depends on position, mass, and context. Even light itself, moving at a constant speed, experiences delays when traveling through curved space-time. Shapiro delay, observed when radar signals pass near massive planets or the Sun, demonstrates that gravity affects the passage of light, and therefore the timing of events. The delay is small but measurable, confirming that gravitational fields alter the flow of time for all processes, not just clocks. Time, in this sense, is inseparable from the structure of the universe. The implications of gravitational time dilation extend to understanding cosmic events. Accretion disks around black holes emit light and radiation that can be measured from Earth. The timing, intensity, and energy of emissions reflect the extreme curvature of spacetime near the event horizon. By analyzing these signals, astronomers can reconstruct the environment and dynamics near black holes, indirectly observing how time slows under intense gravity. Each photon carries temporal information encoded by the curvature it has traversed. In summary, gravity is a sculptor of time. From Earth-based measurements to the edges of black holes, it demonstrates that time is not absolute. Clocks tick differently depending on their proximity to mass. Observers in different positions experience distinct rates of temporal flow. In extreme cases, such as black holes, time can appear frozen from an external perspective while continuing normally for a local observer. Gravity does not merely influence motion, it molds time itself, revealing a universe where past, present, and future are not uniform but relative, dependent on location, mass, and perspective. By understanding these principles, scientists can predict time's behavior in all environments, from laboratory scales to cosmic extremes. Gravitational time dilation is not a theory for thought experiments. It is a measurable, observable effect that shapes the universe and defines how events unfold across space. Falling toward a massive object, orbiting a neutron star, or observing light bent by a galaxy cluster are all experiences that demonstrate the flexibility of time. In every case, general relativity confirms that time is an active participant in the cosmic story, influenced by gravity and intimately connected to the structure of space-time itself. The universe is not still. From the earliest observations of galaxies to the most precise measurements of cosmic radiation, scientists have confirmed that the cosmos is expanding. Edwin Hubble first noticed that distant galaxies appear to move away from us, and the farther a galaxy is, the faster it recedes. This observation revealed a universe in motion, stretching across time and space. Expansion is not just the movement of objects through space, it is the expansion of space itself, carrying galaxies, stars, and light along with it. The distances between objects grow, and with them, the measure of time embedded in light from those distant points. Redshift is the evidence that connects distance, motion, and time. Light from distant galaxies is shifted toward longer wavelengths, moving from blue to red as space stretches. This stretching of light is a natural consequence of expansion. The greater the distance, the larger the redshift. By measuring these shifts, astronomers can calculate not only how far galaxies are, but also when the light left them. Observing a galaxy billions of light years away means seeing it as it was billions of years ago. The expanding universe carries the story of time within its very fabric, and light acts as the messenger, preserving the history of cosmic evolution. The expansion of the universe also provides context for the arrow of time. While physics often allows for equations to run forward or backward, the universe exhibits a preferred direction in which events unfold. Entropy, the measure of disorder in a system, grows over time. Stars burn fuel, galaxies collide, and chemical reactions proceed in ways that increase disorder. The increase in entropy establishes the forward flow of time. Without it, the universe would lack a discernible sequence of events, and causality would collapse. Entropy anchors time, ensuring that processes evolve in one direction, from past to future. Thermodynamics is central to this understanding. The laws governing energy and its transformations provide the framework for predicting how systems behave over time. Heat flows from hot to cold, gases expand, and energy spreads. These processes are irreversible at macroscopic scales, giving time its directionality. The universe, though vast and complex, follows these rules. Every star that ignites, every planet that cools, and every galaxy that merges obeys the laws of thermodynamics. The forward march of time is the result of countless energy transformations, each small process contributing to the overall increase in entropy. The past is fixed because it is already encoded in physical states and records. Photons traveling through space, planetary orbits, and fossilized structures on Earth are all evidence of events that have occurred. Once an event happens, it leaves marks that persist. The trajectory of a star, the chemical composition of a planet, or the radiation from the early universe cannot be altered. These fixed markers allow scientists to reconstruct history with precision. The universe preserves the past in matter, energy, and radiation. making time a reliable sequence of cause and effect. In contrast, the future remains open. While laws of physics can predict probabilities and trends, the exact outcome of complex systems cannot be known in advance. Cosmic expansion allows for multiple possibilities in the development of galaxies, stars, and planetary systems. Quantum events, the motion of particles, and the growth of structures introduce uncertainty. The arrow of time, guided by entropy, ensures that the future will unfold from the past, but it does not predefine every detail. Expansion stretches space, creating the stage for future events to occur, without violating the sequence that has already been established. Light again plays a role in connecting time and distance. As galaxies recede, photons stretch and arrive at Earth increasingly delayed. By observing these photons, astronomers measure not only the distance, but also the epoch from which the light originated. The expanding universe imposes a natural timeline on all observations. Distant objects appear younger, revealing stages of formation, evolution, and interaction. Expansion ties the measurement of time to the structure of space, linking the speed of light, the motion of galaxies, and the history recorded in cosmic radiation. Cosmic microwave background radiation provides a snapshot of the early universe. This faint glow, originating shortly after the Big Bang, is stretched by expansion across billions of years. By analyzing its temperature, spectrum, and tiny variations, scientists reconstruct conditions from when the universe was only a few 100,000 years old. These observations anchor time to physical processes, demonstrating how thermodynamic evolution unfolds on cosmic scales. The early universe's energy distribution, its cooling, and its density fluctuations all follow the predictable increase in entropy, tracing the arrow of time from the beginning to the present. Stars and galaxies are laboratories for observing time's direction. Nuclear fusion within stars converts hydrogen to helium, releasing energy and increasing entropy. The light emitted carries information about temperature, composition, and motion, yet also encodes time elapsed. Over billions of years, star clusters age, supernovae occur, and galaxies evolve. Each transformation is governed by physical laws, with entropy providing the arrow along which processes proceed. Observing these phenomena is equivalent to reading the universe's timeline, confirming that time's passage is measurable, directional, and irreversible. Black holes, though extreme, also demonstrate the principle. As matter falls into a black hole, gravitational energy converts to heat and radiation. The process increases disorder outside the event horizon, reinforcing the forward progression of time. Inside, from the perspective of a local observer, time behaves differently, but the global entropy of the universe continues to rise. Expansion of space and the accumulation of mass energy ensure that even the most exotic regions of the cosmos follow the arrow of time. Nothing in the laws of physics allows a spontaneous reversal of entropy on large scales. The universe's expansion also influences the flow of time indirectly. As galaxies move apart, interactions become less frequent, reducing collisions and energy exchanges. The decreasing density affects the evolution of cosmic structures. Processes unfold more slowly on a cosmological scale, yet the underlying thermodynamic laws continue to operate. Entropy continues to increase, and the direction of time remains aligned with the progression from past to future. The stretching of space and the expansion of distances preserve the chronological order of events across billions of light years. Even on Earth, the principles of cosmic expansion and entropy connect to daily experience. Heat flows, chemical reactions, and biological growth all follow the same rules observed on cosmic scales. The same laws that govern galaxy formation, star life cycles, and cosmic radiation also determine the timing of natural processes nearby. By understanding entropy and expansion, humans can relate local experience to universal behavior, linking the flow of time in laboratories, forests, and oceans to the evolution of the cosmos. The expansion of space ensures that past events remain preserved in light and matter, while the future is filled with possibilities. Redshift provides a direct measure of distance and time elapsed, showing how the universe grows and evolves. Observations of distant galaxies reveal stages of development inaccessible to direct experience. Thermodynamic laws anchor these processes, ensuring that energy disperses, structures transform, and time progresses. The universe operates as a coherent system, with cosmic expansion, entropy, and energy transformations defining a clear temporal direction. Cosmic expansion also defines limits on what can be observed or influenced. Light from objects beyond a certain distance will never reach us, creating horizons in space and time. These limits separate the observable universe from regions that remain inaccessible, preserving the past within reach while leaving the future undefined beyond the horizon. The universe's growth, combined with the arrow of time, establishes both boundaries and opportunities, marking the limits of observation and shaping the framework for cosmic time travel through measurement and inference. By studying the expanding universe and thermodynamic evolution, scientists understand why time flows the way it does. Past events are fixed and measurable, preserved in light and matter. Future events emerge from present conditions, governed by physical laws and energy transformations. Redshift, entropy, and thermodynamics provide the tools to connect time, distance, and cosmic history. Observing galaxies, stars, and cosmic radiation allows humans to witness the passage of time across scales far beyond human lifetimes. Expansion and entropy are the compass guiding this journey, anchoring time to physical reality and revealing the universe's evolving story. Ultimately, the universe is a record of change. Expansion stretches space and time. Redshift encodes distance and age, and entropy ensures that events unfold in a clear direction. The past is written in light, matter, and radiation. The future emerges, shaped by laws that govern energy and motion. Time is both measurable and directional, connected to the fundamental processes that drive cosmic evolution. By understanding these principles, humans can perceive the flow of history across the universe, witnessing events that occurred billions of years ago and tracing the arrow of time that continues to guide the unfolding of cosmic events. The earliest light in the universe is not the glow of stars, but the faint whisper of the cosmos itself. This light, called the cosmic microwave background, is a relic from a time when the universe was young, dense, and hot. It originates from roughly 380,000 years after the Big Bang, when the first atoms formed and the universe became transparent. Before that moment, light could not travel freely. Photons were constantly scattered by charged particles. Observing this background radiation allows scientists to look directly into the universe's earliest epoch, capturing a moment frozen in time, the first light that could escape into the vastness of space. The cosmic microwave background is remarkably uniform, with tiny variations in temperature and density that reveal the seeds of future galaxies and cosmic structures. By measuring these variations, scientists map the early universe and reconstruct the processes that led to the formation of stars, galaxies, and clusters. The radiation is a record of the universe's infancy, carrying information about its density, composition, and the tiny fluctuations that eventually grew into the structures seen today. It is the earliest visible marker of cosmic history, a message sent across 13.8 billion years of expansion. Before stars and galaxies existed, the universe was a sea of hydrogen and helium ions, a glowing plasma too hot for neutral atoms to survive. Photons were trapped, bouncing among charged particles, unable to travel far. This period, known as the epoch of recombination, ended when temperatures cooled enough for electrons and protons to combine into neutral atoms. At that moment, light was finally free to move unimpeded, creating the cosmic microwave background. Observing this light is like peering through a veil to see the universe as it was before structure emerged, before galaxies clustered and stars ignited. Yet even this ancient light has limits. The cosmic microwave background is the earliest signal available because photons cannot escape from a time before atoms formed. The universe was opaque before recombination, and no electromagnetic radiation from earlier epochs reaches us directly. Scientists can infer conditions before this time using other means, such as gravitational waves or theoretical models, but the limit of observation is fixed by physics. The earliest universe is partly hidden, a frontier defined by the behavior of light and matter in extreme conditions. Despite these limits, the early universe reveals fundamental insights into time itself. The flow of time emerges from the changing conditions of space, energy, and matter. As the universe expands and cools, physical processes become possible that were forbidden in the dense, hot early state. Atoms form, photons travel freely, and matter begins to clump under gravity. These transitions define a temporal order, establishing cause and effect sequences that anchor the universe's history. Time is not an abstract backdrop, but a property that evolves alongside the cosmos. Observations of the cosmic microwave background provide a timeline for the universe's first moments. The tiny ripples in temperature correspond to density variations that existed at the time of recombination. These ripples are the blueprint for the large-scale structure of the universe. By studying them, scientists determine the relative proportions of matter, and dark energy, the parameters that govern cosmic expansion and the progression of time. Each photon carries information about its origin, preserving a snapshot of conditions that existed nearly 14 billion years ago. Beyond the microwave background, the universe enters a period often called the cosmic dark ages. During this time, no stars had yet formed, and the universe was filled with neutral hydrogen. Light from this period is extremely difficult to observe directly, but its influence is detectable through the imprint it leaves on later structures. The growth of fluctuations in density, seeded in the first moments after the Big Bang, governs where the first stars and galaxies will appear. Even in apparent darkness, the early universe is alive with physical processes that shape the flow of time and matter. As the first stars ignite, they begin to ionize surrounding hydrogen, ending the cosmic dark ages and illuminating the universe. These earlier stars, composed primarily of hydrogen and helium, mark the transition from a simple, uniform cosmos to a complex, evolving one. Observing the light from these first stars allows astronomers to see the universe as it emerged from darkness, revealing how time and physical processes interact to create structure. Each new observation pushes humanity closer to understanding the sequence of events that defined the earliest eras of cosmic history. The early universe also demonstrates the emergence of physical laws in action. Thermodynamic processes, nuclear reactions, and gravitational interactions define the sequence of events. The expansion of space, the formation of atoms, and the release of radiation all follow predictable rules. Time is woven into these processes, unfolding as events occur in a sequence. Without these changes, there would be no temporal progression. The very nature of time is tied to the evolution of matter and energy in the cosmos, from the first photons to the formation of stars and galaxies. Limits of observation in the early universe are not merely technical, but physical. No instrument can detect photons from before recombination, because light could not travel freely. This establishes a natural boundary for visible time, a horizon beyond which direct observation is impossible. Models of cosmic inflation and the first fractions of a second after the Big Bang rely on indirect evidence, such as patterns in the cosmic microwave background and the distribution of galaxies. Even so, these models are grounded in measurable phenomena, allowing scientists to reconstruct the early universe with remarkable precision. Time near the origin of the universe is fundamentally connected to its conditions. The universe's density, temperature, and expansion rate determine how quickly processes can occur. As the cosmos cooled, different reactions became possible, from the formation of the first atoms to the ignition of stars. Each step defines a temporal sequence, demonstrating that the progression of time is intertwined with the evolution of physical conditions. The arrow of time emerges naturally from these early processes, linking the universe's birth to the unfolding of events billions of years later. Observing the cosmic microwave background requires extreme sensitivity. Instruments detect variations in temperature of only a few millionths of a degree. These tiny differences encode information about density fluctuations, the relative amounts of matter and energy, and the conditions that led to galaxy formation. Each measurement extends humanity's reach backward in time, revealing the structure and evolution of the universe when it was young and simple. The patterns in the radiation are a roadmap for cosmic history, preserving the first moments in a form that can be studied and understood. The transition from a uniform plasma to a structured universe illustrates how time is recorded in physical processes. When atoms formed, photons were freed, and matter began to collapse under gravity. Events unfolded sequentially. Each change depended on previous conditions, creating a chain of causality that links the present to the earliest epochs. Time emerges from these sequences, not as an abstract measure, but as a reflection of real events and evolving conditions. The early universe sets the template for the flow of time observed across cosmic scales. Even after the first atoms formed, light from the early universe is stretched by expansion. Photons emitted billions of years ago are now shifted into microwave wavelengths. This redshift is both a record of distance traveled and a measure of the universe's age. Observing this light allows scientists to calculate the timing of events, the rate of expansion, and the evolution of cosmic structure. The earliest light is therefore a tool for reading the universe's clock, linking distance, time, and history in a single observation. The limits of observation emphasize the connection between physical conditions and time. Before recombination, the universe was opaque. No direct measurement of light is possible. Afterward, light travels freely, carrying information about past conditions. This boundary defines the earliest visible moment, making the cosmic microwave background a natural horizon of time. Everything beyond it is inferred, modeled, and reconstructed, but the observable history begins with this first light, marking the point where time became accessible through photons. The first structures in the universe also demonstrate how time and physical processes are linked. Small variations in density grew under gravity, eventually forming stars, galaxies, and clusters. These formations took millions of years, yet each step followed predictable rules. The unfolding of these events records time in a measurable sequence. Observing galaxies billions of light years away is equivalent to looking back to these stages of formation, witnessing time itself in action. The universe preserves its history in the structure of matter, the light emitted, and the arrangement of energy across space. Time in the early universe is inseparable from cosmic evolution. The expansion of space, the formation of atoms, and the release of light define a temporal order. Without these changes, there would be no progression, no distinction between past, present, and future. Observing the earliest light allows humans to trace this progression, understanding how time emerges naturally from physical conditions. The universe's history is written in photons, in density fluctuations, and in the first atoms, preserving a record of the earliest moments that define all subsequent events. Even today, studying the early universe informs understanding of time. By examining cosmic microwave background radiation, scientists refine models of cosmic evolution, expansion, and structure formation. Each observation connects the present to the distant past, revealing how matter, energy, and radiation evolve. Time is not only a measure of duration, but also a feature that emerges from the sequence of cosmic events anchored in physical processes that began with the first photons and the formation of the first atoms. Ultimately, the early universe serves as both a destination and a record of time. Observing the cosmic microwave background allows humans to witness the universe's infancy, to see the first light, and to understand the emergence of temporal order. Limits of observation mark the boundary between what can be seen and what must be inferred. Time itself arises from these early conditions, from the formation of atoms, the release of photons, and the sequence of events that laid the foundation for stars, galaxies, and all cosmic structures. The earliest universe is a window into the origin of time, a testament to the intimate connection between physical processes and the flow of history. Extreme cosmic environments reveal time in ways that are impossible to experience on Earth. Neutron stars, for example, are remnants of massive stars that have collapsed under gravity. Their cores pack more mass than the Sun into a sphere only a few kilometers across. The gravitational field at the surface is immense. Time near a neutron star passes more slowly than it does for distant observers. If a clock could be placed on the surface, it would tick slower compared to one far away. The difference is measurable, though not as dramatic as near black holes. Yet even this small effect demonstrates that dense objects compress time, bending it alongside space in accordance with general relativity. Neutron stars often spin rapidly, with some completing hundreds of rotations every second. The combination of gravity and rotational speed creates unique conditions for time dilation. Particles in the star's magnetosphere move at relativistic speeds, and clocks attached to them would experience further slowing. Observers far from the star would see signals from these fast-moving regions appear stretched in time. The interplay between strong gravity and high-speed motion amplifies relativistic effects, showing how both mass and velocity shape the flow of time. Accretion disks surrounding neutron stars and black holes are laboratories for extreme time effects. Gas and dust spiraling inward accelerate to near-light speeds before crossing the inner edge of the disk. Friction and magnetic forces heat the material, causing it to radiate energy across the spectrum. To a distant observer, clocks in the disk tick more slowly, due to a combination of gravitational and velocity-based time dilation. The light emitted is shifted and delayed, making rapid processes appear slower and stretched. The disk is a natural demonstration of relativity in action, combining motion, gravity, and radiation to alter perceived time. Black holes are the ultimate environment for extreme time. Near the event horizon, time slows dramatically relative to a distant observer. If a spaceship were to approach a black hole, its crew would experience seconds, minutes, or hours normally. Yet from far away, it would appear to hover at the edge, moving ever more slowly, almost frozen in time. Signals emitted from the ship become increasingly redshifted, stretching toward longer wavelengths until they are no longer detectable. The passage of time depends entirely on perspective. What is normal for a local observer can seem nearly halted to someone farther away. This disagreement among observers is a central feature of relativistic physics. Two observers in different positions experience different rates of time, yet both are correct in their own frames of reference. Relativity does not allow a single universal time. Instead, time is local, shaped by gravity, motion, and position. Near a black hole, this difference is extreme, illustrating how flexible and context-dependent time can be. One observer's seconds can correspond to years for another, a divergence that challenges intuitive understanding, but aligns perfectly with Einstein's equations. No signal escapes certain time regions, particularly beyond a black hole's event horizon. Light, matter, and any form of information are trapped. From the perspective of an external observer, the interior remains hidden forever. Time inside the horizon continues normally for local observers, but the outside universe sees no further events. This creates a boundary where the flow of information stops. The laws of physics inside the horizon operate under the same principles, but communication with the outside is impossible. In this way, black holes define regions where time and causality are effectively cut off from the rest of the universe. The effects of gravity on time are cumulative. Neutron stars, accretion disks, and black holes provide environments where both gravitational and velocity-based time dilation occurs simultaneously. Material moving at near light speeds in strong gravitational fields experiences a double effect. Clocks tick slower due to speed and gravity. Observers measuring signals from these regions see a blend of delays and redshifts, revealing the complex ways that extreme conditions shape time. Understanding these processes is essential for astrophysics, helping scientists interpret the light and radiation that reaches Earth. Even in less extreme cases, relativistic effects near dense objects are measurable. Pulsars, spinning neutron stars emitting periodic signals, provide natural clocks. Observers on Earth detect variations in pulse timing caused by gravitational time dilation and motion. These measurements allow precise determination of mass, density, and the behavior of matter under intense gravity. Each pulse is a message across time, influenced by both position and motion. By studying these signals, astronomers can reconstruct the temporal dynamics of some of the universe's densest objects. Accretion disks also demonstrate the interplay of velocity and gravity on time. As matter spirals inward, it accelerates, experiencing significant time dilation. The closer it gets to the central object, the slower time passes from the perspective of a distant observer. Light emitted from these regions carries the imprint of both speed and gravity. X-rays, visible light, and radio waves all provide information about the timing of events. Observing the disk is equivalent to reading a clock distorted by extreme conditions, revealing the connection between physics and temporal perception. Black hole mergers offer another window into extreme time effects. Gravitational waves, Ripples in spacetime generated by the collision of massive objects propagate outward at the speed of light. The waves carry information about the event's timing, intensity, and mass distribution. Observers detect the signals with delays corresponding to the distance traveled, further illustrating how time and space are intertwined. The process highlights how extreme cosmic events encode temporal information in ways observable across billions of light years. Time inside a black hole remains normal for local observers, but is inaccessible to outsiders. The singularity represents a point where density becomes infinite and space-time curvature diverges. Physics as we know it breaks down at this limit. For those outside, the singularity is unreachable, a theoretical boundary marking the extreme of time's flexibility. The experience of time within these environments is defined entirely by local conditions, independent of external measurements, demonstrating the relativity of temporal experience. Observers outside extreme objects must rely on indirect measurements. Light bending, redshift, and time delays provide clues about processes near neutron stars and black holes. By analyzing these signals, scientists can reconstruct the timing, motion, and energy of events. Observing accretion disks or pulsar rotations allows measurement of time's dilation, even when direct observation is impossible. These measurements confirm the predictions of general relativity and reveal the consistency of physical laws under extreme conditions. The interaction of gravity, motion, and light produces unique phenomena. As matter orbits a black hole, relativistic effects distort signals. Light emitted from the inner edge of an accretion disk is stretched, delayed, and shifted in frequency. Observers perceive time differently depending on position and motion. The combination of strong gravity and high-speed motion creates a natural experiment in relativistic physics, demonstrating the extremes of time compression, delay, and divergence between observers. Even modestly dense stars reveal measurable effects on time. White dwarfs, for example, are dense, remnants of stars with strong gravity at their surfaces. Clocks on or near these stars tick slightly slower than clocks far away. While the effect is small compared to black holes or neutron stars, it is detectable with precise instruments. Every massive object in the universe contributes to shaping the flow of time locally. This principle scales from planets to stars to the densest cosmic objects. Time distortion also influences energy emission. As matter falls toward a black hole, the combination of high speed and gravity slows the local passage of time. Radiation emitted carries the imprint of this delay. Observers receive signals stretched and redshifted, encoding information about the dynamics of infall and orbital motion. These effects are critical for understanding energetic processes such as quasars, X-ray binaries, and relativistic jets, where timing and intensity reveal the influence of time's warping on observed phenomena. Extreme time environments test the limits of physics. Neutron stars, black holes, and rapidly spinning accretion disks provide natural laboratories where both special and general relativistic effects combine. Observations of these objects inform models of gravity, motion, and time. Theoretical predictions match closely with empirical data, confirming that time is not absolute but context-dependent. These cosmic laboratories extend human understanding of temporal physics far beyond Earth-bound experiences. No signal can escape from certain regions, particularly beyond event horizons. Light, matter, and information are trapped, effectively creating a boundary in time as well as space. While the local experience of time continues normally, outsiders see a frozen moment, an eternal approach toward the horizon without completion. These boundaries demonstrate the ultimate consequences of extreme gravity on temporal perception, highlighting the limits imposed by physics on observation and communication. Finally, studying extreme environments provides insight into the nature of time itself. Observers see how gravity and motion distort its flow, how local clocks differ from distant clocks, and how light and information are affected. Neutron stars, accretion disks, and black holes reveal the elasticity of time, demonstrating that it is a physical quantity shaped by mass, motion, and gravity. Time is not uniform or universal, but flexible, responding to the conditions of the cosmos and illustrating the boundaries of what can be experienced or observed in extreme regions. Time is not just an abstract idea. It is something humans can measure and experience differently depending on conditions. Even in low Earth orbit, astronauts experience time differently than people on the surface. Moving at high speeds and slightly farther from Earth's gravitational center, they age a little slower. The difference is tiny, fractions of a second over months, but it is measurable. Every second in orbit accumulates slightly less than a second on Earth. Human bodies, while not in extreme environments like black holes, still experience relativistic effects, demonstrating that even everyday space travel stretches the flow of time. Precision instruments are central to observing these effects. Atomic clocks, which count vibrations of atoms with extraordinary accuracy, measure time with such precision that tiny differences caused by velocity or gravity become evident. Clocks in orbit, clocks on mountains, and clocks on the ground all tick at slightly different rates. These measurements confirm predictions of relativity, showing that time is flexible even on human scales. Atomic clocks do more than keep time. They allow us to directly observe the influence of motion and gravity on temporal flow. Global positioning systems rely on these principles. GPS satellites orbit Earth at altitudes where both speed and reduced gravity affect clock rates. Without correcting for these relativistic differences, navigational errors would accumulate rapidly. Satellites broadcast their positions and time to receivers on Earth, which must account for the slight slowing of onboard clocks due to both velocity and gravity. In this way, millions of people use time dilation every day, unknowingly benefiting from the effects of relativity. Accurate positioning depends on understanding how time changes with motion and mass. Future space travel will amplify these effects. Traveling at higher speeds, especially near a significant fraction of the speed of light, would cause more noticeable time dilation. A traveler moving close to light speed could experience months or years while decades pass on Earth. Interstellar journeys, even theoretical ones, highlight how motion alone can separate the passage of time for different observers. Time travel into the future is not science fiction. It is a real, measurable outcome of relativistic physics. However, there are clear limits. Humans cannot reach light, speed, and the energy required for near-light speed travel is beyond current technology. Time displacement remains modest in practical terms, but it is real. Astronauts and satellites demonstrate the principle on smaller scales. Even if humans never journey to other stars, technology allows us to measure, predict, and account for time differences. Relativity becomes not just theory, but part of everyday science, observable in laboratories, satellites, and spacecraft. The combination of velocity and gravity shapes time in ways humans can exploit for measurement. Experiments have placed atomic clocks on high-speed jets, rockets, and satellites, confirming that motion and gravitational position alter the passage of time. The results align with predictions from Einstein's theories, showing a universe where time is not universal, but dependent on local conditions. Human technology has advanced to the point where time is a tool, not just a backdrop, allowing us to quantify differences in passage and verify extreme physics. Time dilation also affects communications in space. Signals sent between Earth and orbiting spacecraft must account for slight delays due to both distance and time differences. These corrections are minor but critical for precise operations, navigation, and data integrity. Even small variations invisible to everyday perception become important when timing must be exact. Technology has made human timekeeping so precise that relativistic effects are no longer theoretical. They are practical, impacting daily operations in spaceflight and satellite management. Astronauts themselves experience this in a tangible way. Long-duration missions to the International Space Station result in minuscule differences in aging compared to people on Earth. This is a real effect, not just an idea. While the difference is measured in milliseconds over months, it demonstrates that human bodies follow the same relativistic laws as clocks and photons. Time passes differently for those moving and positioned differently in a gravitational field, and humans are now capable of detecting and verifying these differences. GPS is a particularly striking example of daily relativistic corrections. The system functions by synchronizing time between multiple satellites and receivers on Earth. Uncorrected clocks would drift, causing errors in positioning on the order of kilometers each day. Engineers account for both gravitational time dilation from altitude and motion-based dilation from orbital velocity. Humanity relies on these corrections constantly, demonstrating that the effects of relativity are not only measurable, but also essential for modern life. Time separation becomes more pronounced as speeds increase. Any journey approaching a significant fraction of light speed would result in travelers aging more slowly than those left behind. The faster and farther one travels, the greater the temporal gap. Even missions to nearby planets could, in principle, create measurable differences in elapsed time between astronauts and people remaining on Earth. The effect is cumulative, growing with speed and duration, making time travel into the future a scientifically real phenomenon. Despite these possibilities, physical limits remain. Humans cannot survive the energies and accelerations required to reach extreme velocities. Life support systems, radiation, and energy requirements impose strict boundaries on practical time displacement. Nevertheless, even small-scale effects, like those experienced by astronauts and satellites, illustrate the principle clearly. Human technology allows us to witness, predict, and use time dilation, even without leaving the solar system. Observing these effects provides perspective on larger cosmic time differences. If humans could travel near relativistic speeds for long durations, the time experienced would diverge significantly from that on Earth. Future explorers moving at high velocity would return to a world older than the one they left, illustrating a tangible connection between motion, gravity, and temporal separation. Relativity is not just an abstract theory. It is a measurable part of human experience, realized through technology and observation. Time in human technology is therefore both practical and profound. Atomic clocks, satellites, and spacecraft allow precise measurement, correction, and understanding of time differences caused by motion and gravity. GPS is a daily application. Astronauts aging differently are a measurable outcome, and potential interstellar journeys show how time separation could grow dramatically. Humanity has moved from observing time as a constant to understanding it as flexible, measurable, and influenced by motion and mass. The limits of human time displacement define what is possible. We cannot travel back to previous moments, and moving far into the future requires speeds beyond current capabilities. Yet within these bounds, technology allows humans to witness real-time differences. Atomic clocks and satellites prove that the flow of time is not uniform, while spaceflight demonstrates the principle on human scales. Even modest time dilation confirms that relativistic physics is not theoretical, but a reality integrated into practical systems. Finally, human technology bridges observation and experience. Measuring time differences caused by speed or gravity provides insight into the universe's deeper workings. Astronauts, satellites, and clocks illustrate that time is local, dependent on position and motion. These tools show that time travel into the future, while limited by technology, is a real consequence of the laws of physics. Humanity can both observe and experience these effects, demonstrating the profound interplay between motion, gravity, and temporal flow. In essence, the universe provides natural experiments in time dilation, and human technology allows us to participate in them. The principles of relativity are not distant concepts, but observable realities. GPS navigation, satellite operations, and astronaut experiences all demonstrate that time is flexible. Future space travel, though constrained, would extend this flexibility. Human understanding, measurement, and participation in relativistic time effects illustrate the tangible connection between physics, technology, and the passage of time itself. Time, when measured by humans, is no longer uniform. Our instruments, our spacecraft, and our experiments reveal that movement and gravity directly affect its flow. Even minor differences, like those in orbit, are real, measurable, and significant. Human technology transforms abstract concepts into practical observation, showing that relativity governs everyday systems as well as extreme cosmic phenomena. The gap between theory and experience narrows as humans explore, measure, and adapt to the relativistic nature of time. In conclusion, human technology demonstrates that time travel into the future is real, measurable, and predictable. While the limits of speed and survival prevent dramatic leaps, astronauts age differently. Atomic clocks record subtle variations, and GPS corrections operate constantly. Motion, gravity, and technological precision combine to create a framework where time is flexible, local, and verifiable. Humanity's ability to detect, predict, and experience these effects marks the intersection of theory and practical reality, revealing that time itself is part of a measurable, observable universe. Traveling to the past is fundamentally different from moving into the future. While relativity allows future time travel through motion and gravity, going backward is blocked by the very structure of space-time. The universe obeys a strict order of cause and effect. Every event has a cause that precedes it. If an effect were to happen before its cause, the sequence of events would be disrupted. Physics does not forbid backward travel as a story. It is forbidden because it would break the rules that govern reality. The fabric of space-time enforces a consistent timeline, preventing contradictions. Paradoxes illustrate why the past is inaccessible. Consider the famous scenario where someone travels back and prevents their own birth. Such a situation is not merely a thought experiment. It represents a physical impossibility. If an action in the past could change the cause of that action, the chain of events would collapse. The laws of physics are structured to protect causality. Energy, matter, and information all follow sequences that cannot reverse without destroying consistency. Any attempt to alter the past would violate these principles, making backward travel inherently unstable. Space-time itself reinforces this limitation. General relativity describes the universe as a four-dimensional fabric where time and space are intertwined. While warping space-time can stretch or compress time, it does not provide a way to create a closed loop that returns to an earlier moment without catastrophic consequences. The geometry of the cosmos allows for time differences between observers, but all sequences remain ordered. Gravity, mass, and motion can bend time, yet the structure always preserves causality. Wormholes and closed time-like curves have been proposed as theoretical means to travel into the past. A wormhole is a bridge connecting two points in space-time, potentially allowing shortcuts through space. In theory, if one end moves relative to the other or experiences different time flow, a traveler might return to an earlier time. Yet these constructs are highly unstable. Any matter entering a wormhole would likely collapse it or produce uncontrollable energy effects. The universe prevents the formation of stable pathways to the past. Wormholes exist only as mathematical solutions. In reality, they would be destroyed by their own physics. Closed time-like curves, which loop through space-time, also face instability. Even in idealized models, tiny disturbances or quantum effects could destroy the path. Energy requirements alone are immense, exceeding anything achievable by matter or technology. The equations suggest possibilities, but physical reality intervenes. The universe has built-in protections that prevent paradoxical loops from forming. These limits are not arbitrary. They are necessary for the consistency of all physical laws. Physics protects cause and effect in more subtle ways as well. Signals and information cannot propagate faster than light. This restriction ensures that no message or object can arrive before it is sent. Any attempt to violate this limit would break relativity and produce contradictions. Light cones, the paths that light and causality define through space-time, set boundaries for what can influence what. Every event lies within a light cone of its causes, preventing retrograde influence. Time travel to the past would require leaving this cone, something physics does not allow. Even advanced theoretical constructs fail under scrutiny. Negative energy, exotic matter, and space-time manipulations have been suggested to stabilize backward travel. Yet all require conditions that cannot exist for more than infinitesimal moments, if at all. The universe enforces its rules through energy constraints, quantum effects, and the inherent structure of space-time. Attempting to travel backward would require circumventing every one of these protections simultaneously, a feat far beyond any physical possibility. Quantum physics also supports the impossibility of past travel. While uncertainty allows strange behaviors at microscopic scales, macroscopic systems preserve causality. Particles can fluctuate and interact unpredictably, but overall, cause precedes effect. Entropy increases, sequences unfold, and energy transformations proceed in a forward direction. The arrow of time, linked to thermodynamics, adds another layer of protection. Even if one could manipulate space-time locally, the global increase in entropy prevents reversal of events. Time machines, as imagined in fiction, cannot exist under these laws. No machine can rewind history without violating energy conservation, quantum stability, and relativistic causality. Physical laws are not negotiable. They create a consistent framework in which events unfold predictably. Every particle, wave, and photon follows the rules of this framework. Backward travel would require overriding these fundamental principles, which the universe does not allow. The impossibility of traveling to the past does not preclude observing it. Light and radiation carry information from earlier times, effectively letting humans witness history without interfering. Telescopes, satellites, and detectors act as time windows. Looking at distant stars or the cosmic microwave background allows scientists to see the universe as it was, safely separated by the limits imposed by light travel and causality. Observation is permitted, interference is not. Even if wormholes or other exotic structures could exist momentarily, practical access is beyond reach. The forces, energies, and precision required to stabilize such pathways exceed all technological limits. Any attempt to enter a closed time-like curve would likely destroy both traveler and structure. These limitations ensure that the past remains untouchable, preserving the sequence of cause and effect on which the universe depends. In short, traveling to the past is forbidden not by imagination, but by necessity. The laws of physics enforce causality, maintain the arrow of time, and prevent paradoxes. Wormholes and hypothetical constructs illustrate potential pathways, but fail when real physics is applied. Time travel into the past remains beyond the domain of possibility, firmly constrained by energy, quantum effects, and the structure of space-time itself. Humans can explore time through observation, measurement, and forward travel. Looking back, observing the cosmic microwave background, or measuring distant starlight provides access to the past without altering it. These observations confirm history while protecting causality. The universe provides windows into its own history, but does not allow interference. Time remains directional, ordered, and consistent, ensuring that the past is preserved even as the future remains open. Understanding these limits helps clarify the nature of time. The past is not a landscape to traverse. It is a record, encoded in matter, energy, and radiation. Physics safeguards this record, preventing paradoxes and ensuring continuity. Attempts to reach backward moments collide with the universe's inherent rules. The impossibility of past travel is therefore a reflection of the consistency and stability of the cosmos, not a failure of imagination. Current science allows remarkable access to the past through indirect observation. Light from distant galaxies, gravitational waves, and cosmic background radiation all provide insight into earlier epochs. Yet all of this remains passive. Humans can observe and measure, but cannot change what has already occurred. Time travel into the past is strictly off limits, a boundary enforced by the very laws that allow future travel and forward progression. Ultimately, the universe maintains a strict separation between past and future. While motion and gravity can warp time, and while future time travel is possible in principle, retrograde movement remains forbidden. The combination of space-time geometry, energy limits, quantum effects, and the arrow of time ensures that backward journeys are impossible. Humans can measure, predict, and witness time, but they cannot rewrite it. The past is permanently fixed, preserved by the unyielding rules of physics. In conclusion, traveling to the past is blocked by nature itself. Causality, space-time structure, and thermodynamic laws all enforce a one-way flow. Wormholes and theoretical time loops collapse under real conditions. Paradoxes are not mere stories, but reflections of physical constraints. Observation of the past is allowed, interference is not. The universe protects its history, ensuring that cause and effect remain intact and that time maintains its directional order across all scales. From the vantage point of the cosmos, Earth exists for only a fleeting moment. Compared to the universe's nearly 14 billion years, human history is a blink. Continents shift over millions of years, stars are born and die over billions, and galaxies collide across eons. Civilization, in this vast timeline, occupies a tiny fraction. Our cities, technologies, and achievements appear and vanish in the context of cosmic time. Yet even in this brief interval, humans have learned to measure, understand, and reflect on the flow of time, connecting fleeting experience to the grand narrative of the universe. Observing time on cosmic scales changes perspective. Ancient light from distant stars reaches telescopes, allowing humans to witness events that occurred long before the first civilizations. The birth of stars, the formation of galaxies, and the echoes of the early universe are all accessible through careful measurement. This understanding does not alter destiny. It situates humanity within a larger ongoing story. Awareness of time's immensity inspires reflection, humility, and curiosity. Even though humans cannot control cosmic processes, they can study and interpret them, finding meaning in observation rather than interference. Civilization itself is shaped by time, both human and cosmic. Societies rise and fall, inventions occur, and knowledge accumulates, all against the backdrop of planetary and stellar evolution. Earth provides the conditions for life to persist only briefly in cosmic terms. Recognizing the scale of time encourages a long-term perspective on science, exploration, and preservation. Humanity's awareness of temporal flow, from seconds to millennia, bridges the brief span of experience with the enormous scale of the cosmos, highlighting both fragility and opportunity. The universe continues to evolve without awareness of observers. Stars ignite and burn out, black holes grow, and galaxies drift apart, entirely indifferent to human existence. Time flows according to physical laws, unaffected by consciousness or desire. Light carries messages from distant events, but these are passive signals, not interventions. Understanding the universe's progression emphasizes that human activity is momentary within an immense, ongoing sequence. Knowledge does not change the universe's evolution, but it allows observers to contextualize their place within it. Time travel, when considered in human terms, is largely observational. Telescopes, satellites, and detectors allow glimpses into the past, letting humanity witness events across billions of years. These observations are a form of temporal exploration, revealing history without disrupting it. Light, gravitational waves, and cosmic radiation provide records of what has occurred, preserving the sequence of events. In this sense, time travel is less about moving through moments at will, and more about understanding and experiencing them through careful measurement and reflection. Even on Earth, the passage of time shapes human experience. Clocks, calendars, and technological devices measure intervals and coordinate activities. These tools are extensions of the same principles that govern the universe. Human timekeeping is a small-scale reflection of cosmic time. Understanding relativity, expansion, and gravitational effects extends perception beyond everyday experience, connecting the seconds of life to the billions of years of the universe. Time becomes a lens through which humans interpret both immediate and distant phenomena. The brief duration of human presence in cosmic time underscores the value of knowledge. While life spans decades or centuries, understanding the universe provides continuity beyond individual existence. Observation allows humans to witness events far older than life itself, creating a bridge between personal experience and cosmic history. This perspective fosters both humility and wonder, emphasizing that insight into time is possible even in a transient existence. Cosmic time also informs scientific exploration and future possibilities. Understanding the speed of light, relativistic effects, and gravitational influence enables predictions about the future trajectory of stars, galaxies, and the universe itself. While humans cannot alter these outcomes, studying them reveals patterns, causes, and relationships across immense spans. Time travel in this sense is a tool for understanding, not an escape from reality. Observation allows participation in the unfolding universe, even without control over its progression. Earth's momentary place in time provides a frame for reflection. From this perspective, human endeavors, while brief, are meaningful in terms of understanding. Spacecraft observe distant objects, telescopes capture ancient light, and instruments measure gravitational waves, all extending perception beyond personal and planetary limits. Knowledge of time's vast scale situates humanity in context, highlighting the difference between personal and cosmic duration, while showing how comprehension bridges the two. Finally, recognizing humanity's position in cosmic time underscores a fundamental truth. Time is vast, structured, and indifferent, yet accessible through careful observation. Light from distant epochs, measurements of motion, and understanding of physical laws allow humans to perceive the universe's history. Time travel, therefore, is less a matter of escape or alteration, and more an opportunity to observe and reflect. Humanity's brief presence in the cosmos is framed and enriched by this understanding, connecting the fleeting to the eternal, the observer to the vastness, and human awareness to the ongoing flow of universal history.